Everybody, welcome to our third ed puzzle lesson of quarantine. Today we're going to talk about Kirchoff's law and parallel circuits. Two-part lesson today because in order to understand parallel circuits, we're going to have to understand this idea of Kirchoff's law. Let's start with what a parallel circuit is. A parallel circuit has a branch off of the main line. So in a series circuit, everything was along the same exact route, right? There was just one pathway, and all of the electrons traveled on the same pathway in a series circuit, right? This is in a series circuit. In a parallel circuit, you have multiple branches that the electrons can travel. So in a parallel circuit, you have it kind of branching off into different ways. There's a lot of different advantages to using a parallel circuit instead of a series circuit, where it branches off like this. One such advantage is, let's say there was a break in the line here. Let's say this broke the line right there. Well, will R3 still work? The answer is no. There's no continuous pathway for R3 to work. But what about R1 and R2 here? Will those still receive a current? The answer is yes. You'll still get a current through these lines, even though there's a break right here. Whereas in a series circuit, if this were to go out, the whole thing would shut down. This is the difference between you turning off your light and then suddenly the hospital down the street losing power, which is obviously not ideal. So for the most part, you're going to see these parallel circuits in the world here. They're very common. You're going to see series circuits, though. They're cheaper. That's the advantage of a series circuit. You're going to see it where price is a priority more than everything else working. Very common series circuit is like in Christmas bulbs, where they don't care. One goes out, the whole string goes out, whatever. Parallel circuits are mostly what you're going to see in your house, in the streets, and in most electrical systems that we're going to use in the real world. They're more expensive, but the advantage is if you have a break in your line like this or a switch, it doesn't shut down the whole system. There's another advantage to using parallel circuits that we're going to talk about very soon. But first I want to talk about Kirchoff's law. Kirchoff's law is very simple. It's a conservation of energy rule. However much current you have going into a system is the same as the current that is leaving that system. The current in is equal to the current out. I'm going to draw a brief example here. Let's say we had a couple of wires, and look at the directional arrows I'm going to give you here. This is going in, and we'll have this one also going in here. And we'll say this is like 3 amps, and this is like 2 amps, right? The current coming out here, after these converge, 3 and 2, has to be equal to the current going in. How much current are we going to have going in? 3, 2, 5. So we'd have to have 5 amps out. The current in, 5 amps, has to equal the current out, also 5 amps. That's called Kirchoff's law. It's a conservation of energy rule. You could have more complicated versions of Kirchoff's law as well. Let's say, for example, we had multiple branches here. So we'll say this one has an arrow here, and we'll say the ammeter here. I'm going to start drawing these as ammeters. So the bulbs will actually be inside of the current. So we have 4 amps here. And notice the arrow I drew for us. That's going to show us whether it goes into the node or out of the node. The arrows are very important here. And we'll have another one down here. And we'll say this is a 3 amp current. And let's say there are 2 branches out here. 2 branches out. And we'll say this one is 2 amps. And this one is also out. And the question is, what is the current going to read here? Well, we have 7 amps in, 4 plus 3 in, right? So we have 7 amps in. And right now we have 2 out. So we're going to have to add another 5 amps out. So that way we add up to 7 amps out. 7 in, 7 out. Current in is always equal to current out. And that's Kirchoff's law. You want to make sure that however much current you have going into a node, that's right here, this is called a node, your current in has to equal your current out. That's always true. That's Kirchoff's law. That's going to bring us to parallel circuits. Let's start talking about a parallel circuit. A parallel circuit has all these different branches that current can travel through. So we see it has all these different branches that current can travel through, right? Our current is going to split up down these different branches. And that brings us to our first rule for a parallel circuit. First rule for a parallel circuit, opposite of a series circuit. Your total current, I total, is equal to I1 plus I2 plus I3, and so on, indefinitely. This rule is, of course, on page 4 of your reference table. We can find that on page 4 of our reference table there under parallel circuits, our first rule. I total is equal to I1 plus I2, and so on in a parallel circuit. All that means is the current down these different branches, 1, 2, 3, has to add up to the total current here before it splits off. So if I put an ammeter here, it's going to say the same thing as this current plus this current plus this current. And we'll look at those specific values very soon. Our next rule for current is everything has a direct path back to the battery. Take a look here. We have a direct path back to the battery to R1. We have a direct path back to the battery for R2. We have a direct path back to the battery for R3. They all have a direct connection back to the battery, which means that this voltage here is constant for all 3 branches. So voltage is the same everywhere in a series circuit. V total equals V1 plus V2 equals V1 equals V2 equals V3. This is the same as what in a series circuit? This is the same as current in a series circuit. Voltage, same everywhere in a parallel circuit because they all have a direct branch back to the battery. So that takes care of current and voltage. We're missing one thing here, and that's our resistance. Now, you can solve the resistors individually, okay? And that will work just fine here. You can solve the resistors individually. In fact, let's make a verb chart and do that together here for this particular circuit. Let's make a verb chart and solve out our individual currents using what we know here. So VIRP, and we're going to go down here, and we're going to make it for R1, R2, R3, and then for the total system. And let's take a look at what happens here. First of all, we have R1, R2, R3, 3, 6, and 6. 3 ohms, 6 ohms, 6 ohms. We are not adding these up. In fact, in a parallel circuit, more resistors means less resistance. We're going to talk more about that soon. We also know I wrote this in the wrong column. This should be in the resistance column. So 3 ohms, 6 ohms, 6 ohms. We are not adding these up, all right? We do have a column we can fill out completely right away here, and that's voltage. All the voltages, same throughout. So V1 is going to be 12 volts. V2, 12 volts. V3, 12 volts. And the total system, 12 volts. Excellent. Let's use that, and we can use V equals IR to find our current down each branch. The current here, we say V equals IR. We find R, so V divided by R, we get 4 amps. Here, 12 divided by 6, 2 amps. 12 divided by 6, 2 amps. That's the readings on these ammeters. 4 amps, 2 amps, 2 amps. Notice as resistance goes up, current goes down. As resistance goes up, current goes down. You could write this out as R equals V over I. And as resistance goes up, yes, current goes down for each branch. For each branch. Let's build on that. 4, 2, 2. How do we find our total current for the system? I total is I1 plus I2 plus I3. So we're going to have 8 amps of current here. We can use that to find the total resistance in our system because V equals IR, 12 divided by 8, right? R equals V over I. 12 divided by 8, we get 1.5 ohms of resistance. That's one way to calculate your resistance. And of course, P equals VI, so you can find the power through each part of this too. VI, we're going to get 48 watts through our first one here, 24 watts through our next one, 24 watts to our next one, and remember power corresponds to brightness. And you can even find it for the entire system here, and that's going to be 96 watts here for the whole system. That's all great and good. I want to go back to this 1.5 here. Kind of a weird number. Where's that coming from? The rules that we've talked about so far don't apply to this. You don't just add these. It's not 12 ohms. It's not 12 ohms. So you don't just add them in a parallel circuit. And if we notice here, we're not the same as the original, kind of like voltage in a parallel or current was in a resistance in a series circuit. They're not all the same. So this is a little bit of an unusual number. We might be wondering where this is coming from, this 1.5 ohms. We're going to talk about how to actually calculate this, and what you need to realize here is that more resistors in a parallel circuit means a lower resistance. Look at our resistances here, 3, 6, 6. How do they compare to 1.5? Well, they're all greater than 1.5, meaning adding more resistors, we had a 3, we added a 6, we added another 6, adding more resistors lowered our resistance. The easiest way to think of this is like traffic on a highway. What we added is more lanes to this highway. Yes, these lanes have potholes. Those are the resistors, they have potholes. But more lanes mean it's easier for traffic to flow, which means more current, less resistance. More resistors in parallel means less resistance and more current. Let's talk about how to actually calculate here our resistance, or what's called our equivalent resistance. It's a little bit tricky, probably the most tricky part of this unit. Our equivalent resistance here, let's take a look at how we want to calculate this. We are going to say to ourselves, well, 1 over our equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. There's a bit of a trick on math here. Let's take a look. What you want to do though, 1 over REQ equals 1 over R1, 1 over R2, 1 over R3. We don't know our equivalent resistance. I mean, we do, but we calculated it differently here. We're going to use 1 over R1, which is 3 ohms, R2, which is 1 over 6 ohms, and 1 over R3, which is 1 over 6 ohms. We're going to add these using a least common denominator, or your calculator. Calculator is also fine here. 1/3 plus 1/6 plus 1/6. Our least common denominator is 6. We're going to get 1 over REQ equals 4 over 6 ohms. And because 1 over REQ equals 4 over 6, we have to take the reciprocal of that. And you could do that on the calculator by doing 1 over your answer, which is going to give us here 1 over 4 over 6 is 6 ohms over 4. 6 over 4, which is the same as 1.5 ohms. That's your equivalent resistance. That would be like if we combined all the resistors into one resistor for the entire system. Main rules here. Voltage, same everywhere. Current is going to add up to the total current. More resistors, less resistance, more current, assuming voltage is constant. Remember Kirchoff's law, current in equals current out. That's it for parallel circuits. And let's get some Jimmy time. So you guys can take a look at what's going on the board here. Jimbo. Jim. Ah. Jimmy's not feeling it today. So he'll be here for the next video.